NASA is inviting proposals from private industry for a 100 kilowatt nuclear fission reactor to power operations on the Moon. With nuclear reactors now under active development for use off-world, the next obvious question is, can we use a nuclear reactor for propulsion? The answer is yes. So in this video, I will explore the idea of using a nuclear reactor to power fast transits to Mars and the outer solar system. There are two main types of nuclear transportation in the literature. First, NTP or nuclear thermal propulsion, and second, NEP or nuclear electric propulsion. We'll cover both types in the video, including the advantages of using nuclear for transportation, along with some of the challenges. Then we'll cover why propulsion follows power. That is, it makes sense to build off-world nuclear reactors for power first, before designing them for transportation. Nuclear thermal propulsion, or NTP. In simple terms, a nuclear thermal propulsion rocket, or NTP for short, works by using a nuclear reactor to superheat a lightweight fuel, usually liquid hydrogen. This heat turns the liquid into a high-pressure gas, which then expands rapidly and shoots out through a nozzle at the back of the engine, creating powerful thrust to propel the spacecraft forward. You can think of it as similar to boiling a kettle, just on a larger scale. Instead of a flame or electric element providing the heat, a nuclear reactor is used instead. Unlike a chemical rocket, which burns fuel with oxygen, NTP relies solely on heat, requiring no combustion or oxidizer. NTP engines are about twice as efficient as the best chemical rockets, achieving similar thrust levels while using only 40 to 50% of the spacecraft's mass for propellant, compared to 80 to 90% for chemical systems. This efficiency halves the fuel load or doubles the thrust duration, enabling higher velocities and leaving room for larger payloads, such as scientific instruments or crew habitats. Unlike nuclear electric propulsion, NTP provides high thrust, allowing rapid departures from Earth orbit, crucial for crewed missions. This efficiency also permits launches outside narrow planetary alignment windows, making NTP ideal for outer solar system missions to destinations like Europa or Titan, where robust habitats or landers could be transported, tasks impractical with chemical propulsion. Faster transits reduce crew exposure to radiation and other risks, requiring fewer consumables and allowing more payload for science or technology. NASA aims to limit Mars round trips to 2 years or less to minimize radiation exposure, making NTP a promising solution for efficient, high-thrust space exploration. Nuclear electric propulsion, or NEP. Nuclear electric propulsion, on the other hand, uses a nuclear reactor to generate electricity. Thrust can be generated by adding ion thrusters, scaled up to higher power levels to make use of all the electric power generated by the nuclear reactor. Typically, this will be inert gas such as xenon or krypton. Ionized particles are accelerated to enormous speeds to generate thrust, resulting in highly efficient propulsion, with the side benefit of large amounts of electrical power being available to power the ship's systems and scientific equipment. Unlike chemical thrusters that delivers quick, powerful bursts of thrust, a nuclear electric propulsion engine provides gentler but continuous thrust over a long period of time. This type of nuclear propulsion is well suited for robotic exploration of the outer solar system, as the abundant onboard electrical power can operate a large number of sophisticated scientific equipment, perhaps including active scanning systems such as radar, which typically are too power hungry for existing robotic missions. NEP is best suited for non-crewed missions, due to the low thrust which results in longer transit times. The proposed gateway station that will orbit the Moon will have powerful ion engines for station keeping. These engines could easily be adapted to use a nuclear engine for providing electric power, rather than solar panels. L3Harris is working on the power and propulsion system for the gateway station. Their ion thrusters operate at 12 kilowatts, and are the most powerful electric propulsion system ever developed. An L3Harris spokesperson said, "For a nuclear electric propulsion system, we don't need to change the reactor or the power conversion system. We just need to optimize the radiators to reject heat into space and put electric propulsion systems on the other end, unquote. Nuclear power eliminates the need for large solar arrays, which reduces the mass of the system. Propulsion follows power. Nuclear electric propulsion system is, in simple terms, an electric power system integrated with electric thrusters. A power-first strategy develops and validates the core power system first, before adding an electric thruster component, which is already a mature technology. These thrusters simply require scaling to higher power levels and improved thermal management to function effectively. NASA's planned 100 kilowatt nuclear fission reactor for lunar use will test critical systems essential for nuclear propulsion, including the reactor itself, radiators for heat dissipation, and high voltage power management. Once these components are proven in space, adding electric thrusters and thrust vector controls becomes a straightforward step to create a fully operational NEP system, paving the way for efficient deep space exploration. Human exploration of Mars and Ceres, mission architecture. A paper I linked to in the video description proposes a 4.6-year mission to both Mars and Ceres using nuclear propulsion. A crew of 6 launch in July 2035 from low Earth orbit aboard a nuclear-powered space vehicle. They approach Mars in March 2036, with a transit lasting between 192 and 258 days. 3 astronauts descend to the Martian surface for exploration, while the other 3 continue to Ceres, a dwarf planet in the asteroid belt. The Ceres transit takes approximately 574 days, starting in April 2036, reaching Ceres in November 2037. The crew have 46 days to explore Ceres before heading back to Mars. After another 574 days, they enter Martian orbit. The full crew then departs for Earth, arriving in low Earth orbit by April 2040. Earth-Ceres transfer is estimated at 11.2 km per second, which is achievable with nuclear propulsion. For further details, refer to the mission scenario in the linked paper. Megawatt nuclear reactors are needed for crewed missions to the outer planets. NASA's planned 100 kilowatt nuclear fission reactor for the Moon's surface falls short of powering crewed missions to the outer planets, such as Jupiter or Saturn. These missions require megawatt-class reactors to achieve the necessary performance. However, smaller reactors could support crewed Mars missions, reducing transit times by months compared to chemical propulsion. For crewed missions to the outer planets, transit times must be limited to a few years each way to minimize radiation exposure and resource demands. This requires a velocity change, or delta V, of 10 to 20 km per second beyond Earth escape velocity. A crewed spacecraft weighing hundreds of tons with habitats, life support, radiation shielding, and supplies would require substantial power. Studies indicate that fast transits to Jupiter require a nuclear reactor delivering 300 to 500 megawatts, far exceeding the capabilities of the reactors being developed for NASA's Artemis program. Even for Mars, a 2-year round-trip crewed mission would require a nuclear electric propulsion spacecraft with a power output of 400 kilowatts to 2 megawatts, according to NASA research. While smaller reactors help Mars exploration, megawatt-scale reactors are essential for crewed missions to the outer planets. Advantages of nuclear-powered spacecraft. Fission power systems offer higher power levels compared to traditional solar or chemical power systems, enabling the operation of high-energy scientific instruments and advanced propulsion systems. Unlike solar power, which weakens with distance from the sun, nuclear reactors provide a consistent and reliable energy source, supporting long-duration missions to the outer solar system and its moons. In 2018, NASA successfully tested Krusty, a small nuclear fission reactor designed for space, proving its ability to supply steady power over extended periods. NASA now plans to develop a reactor at least 10 times more powerful than Krusty. Nuclear-powered propulsion systems support fast transits to Mars, reducing the crew's exposure to radiation and other hazards and providing more payload capacity. Challenges with nuclear-powered spacecraft. One of the major limitations of advanced propulsion systems, such as nuclear propulsion or electric propulsion, is the higher initial mass requirements. This can result in an increased launch weight, leading to higher costs for sending spacecraft into orbit or on deep space missions. Traditional systems like chemical propulsion typically have lower mass-to-power ratios, which makes them more favorable for initial deployment. Scaling nuclear propulsion to higher power levels, especially above 100 kilowatts, is complex. High-power nuclear reactors require improvements in materials and heat management. Radiation shielding. Nuclear-based propulsion requires extensive radiation shielding to protect both the spacecraft and crew from harmful radiation. This increases the overall system mass. System mass is a critical issue because nuclear propulsion system components are often heavy in comparison to chemical engines, even without the additional radiation shielding that's required. One alternative to using heavy radiation shielding is to use the abundant electrical power from a nuclear electric propulsion system to generate a magnetic field to surround the spacecraft, offering a viable alternative to heavy passive shields in certain designs. This approach, known as active magnetic shielding, uses superconductor magnets to create a protective field that deflects charged particles from cosmic rays and solar events, similar to Earth's natural magnetosphere. Current concepts indicate it could reduce overall mass, but still requires substantial power and specialized materials. Integrating a magnetic field generator is straightforward in theory, as NEP systems are designed for high-power electric loads. Studies from NASA in 2022 have demonstrated feasible configurations such as a torus, which maximizes the exterior field without interfering with onboard systems. ESA have explored solenoid and pumpkin coil designs, confirming that magnetic fields can effectively shield against particles up to giga-electron-volt energies. Power requirements for active shielding, estimated at 60 to 100 kilowatts, are well within the capabilities of next-generation nuclear reactors. NEP is ideally suited for this, as it already generates substantial electrical power for propulsion. However, this approach trades mass savings for increased system complexity. While a credible path forward, further development is needed to refine and implement active magnetic shielding for deep space missions. Upcoming events. NASA will shortly be asking for proposals for a nuclear power station for the Moon, with a minimum power output of 100 kilowatts. One or more proposals will be chosen for funding, leading to a nuclear reactor on the Moon's surface by 2030. Crewed missions to Jupiter and Saturn's moons become possible depending on how much radiation exposure is acceptable. What are your thoughts on nuclear propulsion for robotic or crewed missions to Mars and beyond? Leave your thoughts and opinions in the comments section below. Thanks for watching. If you enjoyed this space video, consider buying me a coffee to help fund more episodes like this. The link is in the description. Space News Live is on Saturday evening or Sunday morning depending where you watch from. The live stream is a great way for you to share your thoughts and opinions on the videos I posted this week, or on any space topic in general. I highlight the most thought-provoking comments on videos I've received, along with late-breaking space news and previews of upcoming content. If you've got the time, please tune in and say hi. Be sure to like and subscribe so you'll see our upcoming videos. We make videos every week covering the space industry, with an emphasis on the smaller space startups that aren't covered so well on other channels. See you soon.